Hello everybody, Dr. Carroll here. Welcome to Chem 1111 Screencast, Unit 7, Lecture 2. We're talking about multiple bonds today. Double bonds and triple bonds. We're called carbon, nitrogen, oxygen, sulfur, phosphorus are the big ones that use multiple bonds, sigma and pi bonds. Every bond is sigma. The question is there a pi involved as well? If it's a double bond, there's one sigma and one pi. If there's a triple bond, it's one sigma and two pi's. So let me jump to page 319 in our mini text here. Lots of carbon you saw here are going to be, where's my pen? There we go. Are going to have multiple bonding like ethene. Ethylene, yeah, UPEC name is ethene, so C2H4. So we are going to learn that one of the bonds between the carbon-carbon is going to be a sigma bond. That's going to be the carbon sp3 hybrid orbital on this one, overlapping with the carbon sp3 hybrid orbital on the other one. And there will be concentration of electron density along the bond axis between those two carbons. Above and below the plane of the molecule, ethene is a planar molecule, there is also a concentration of electron density, and that is known as the pi bond. So the above and below together make up a pi bond. So it has a sigma bond and a pi bond. Okay, so here we go into nicer pictures of it all. So a ball and stick model, and did I say sp3 hybrid or sp2? Or did I not even say any hybridization? Okay, it's sp2 hybridization. That's what I say. So here we have in the plane, we have the sp2 overlap. The other bonds are sp2 carbon with the 1s on the hydrogen. So that's in the plane. That's all good, consistent with 120-degree bond angles. But what about the other bits of electron density? So here we have the sigma bonds, high electron density distributed symmetrically along the internuclear axis. So the one we were looking there is the carbon. Here is the hydrogen. Here would be for some other molecule. So what can we say about the double bond? You have a p orbital on either carbon that is not involved in the sp2 hybridization. So here's a better view, I think. So you have the plane containing all 6 atoms, 2 carbons and 4 hydrogens, and then you got a p orbital on one carbon talking to a p orbital on the other, reinforcing it on either side's there, and that together makes up a pi bond. So you have sigma bond and pi bond. That pi bond gives it more strength than a single carbon bond. It's also harder for this molecule to rotate around its axis because of the pi bond. So those are different views of the pi bond, and together it makes a double bond. Okay? Well, we're going to see it a different way too. Wow, look at this fancy way here. So you got the carbon here and carbon here, and so we have sp2 hybridized in green, and you see the bonding, and then you have the pi bonding. Now top view, you can only see the top part. Here side view allows you to see those p orbitals talking to each other, that side overlap, and at the bottom too, and that gives you the pi bond. You can have an end view as well. Has nothing to do with the 3.14. Okay. Availability of a leftover valence p orbital to form pi bonds is characteristic of sp2 hybridization. And it's not just carbon, we can have it carbon bonded to nitrogen and other examples, and that's what we do in example 7.6. So you draw the Lewis structure, determine the steric numbers in hybridization, construct the sigma framework, and then deal with the pi bonds. So usually you deal with the pi bonds at the end. So an imine is a molecule containing a C-N double bond. So here it is, an imine, simplest one, and we have here the Lewis diagram, everything's satisfied here. 4, 9, 12, 2, 4, 6, 8, 10, 12. So the carbon is sp2 hybridized. The nitrogen is also sp2 hybridized, which means that each of them have an unhybridized p orbital, and those p orbitals overlap to give us the pi bond. And let's just look at this nice picture here showing it all. So there's the carbon with the 3 sp2 hybridized orbitals, and they overlap with hydrogen. We got 2 hydrogen here. Then you have a carbon sp2 overlapping with a nitrogen sp2. So that gives you a sigma bond between the carbon and the nitrogen. Then we have a lone pair on the nitrogen. And then we have a hydrogen overlapping with the nitrogen. So it's an sp2 with a 1s. So that gives me the framework. Side-by-side overlap with the p orbitals gives the pi bond that completes the bonding description. Okay, so you have a pi bond, and that takes care of that. Okay, chloroethylene, I'm not going to bother with that. I mean, it's just ethene, but you got a chlorine instead of a hydrogen. You can also have pi bonding involving oxygen atoms. So this is going to be on, we did that one, page 322, pi bonding involving oxygen atoms. And here's acetic acid. Acetic acid has a carbon atom, another carbon atom, and an oxygen atom. So there's 3 inner atoms. The carbon at the left is sp3, carbon in the middle is sp2 hybridized, inner oxygen is sp3 hybridized. So sp3, sp2, sp3. Put it all together, and you're also going to see some double bond with a p orbital in the terminal oxygen here. Okay. And then you also have lone pairs on the oxygen. So here we see acetic acid, CH3, there's the methyl group. There's CO, that's the sigma framework. There's to the other O, there's a hydrogen. There you have the lone pairs on the oxygen. And now you have your unhybridized on the carbon and unhybridized on the oxygen, and those give you the pi bond. Okay. Inner oxygen atoms do not participate in pi bonding, except if it's ozone, apparently. Any inner oxygen atom is a steric number of 4 could be described using sp3. So the oxygen is not, neither oxygen is hybridized. The pi bond is formed from the 2p orbital on oxygen with the 2p orbital on carbon. You can read the thing about elephants on your own. And so that was the example for acetic acid. Okay, an interesting question students sometimes ask. They say, well, if carbon can form double bonds, which means a pi bond, shouldn't silicon? Silicon's in the same group as carbon. And it can, it's just much less likely because the distance between the silicon nuclei is much larger than the distance between the carbon nuclei, so the pi bonds don't overlap as easily as they do with the carbon-carbon. For the silicon atoms, the 3p orbitals are too far apart for strong side-by-side overlap. Okay, so you don't find as much pi stuff with silicon. Where do you? Carbon, oxygen, nitrogen. Okay, so that was double bonds. Now let's look at what about triple bonds. And if I'm looking here, triple bonds involve one sigma bond and two pi bonds. So the classic example is acetylene, also called ethine. So acetylene is also known as ethine. So each carbon is sp hybridized because it has two Vesper groups, or two electron groups around it, two bond groups and no lone pairs. Fine, two bond groups and no lone pairs. So we have a linear setup, and here we see the framework for it. You have sp hybridized on one carbon overlapping with sp hybridized on another, and the other sp hybridized orbital on the carbon overlaps with the 1s of the hydrogen on the left and overlaps with the 1s hydrogen on the right. And then you have these two other p orbitals, which are perpendicular to the sigma, and so those both form pi bonds. So that's why you get two pi bonds. Okay, here you have a px unhybridized on one carbon with a px unhybridized on the other, and then you have the py coming out. So you end up with both of them. And here's a beautiful picture, it looks like a hot dog or something, showing the composite orbital overlap view of the sigma and pi bonds of acetylene. So you have the blue and the red going down and the blue and the red going across. Those are my two pi bonds, and then all the way through the middle there, that is my sigma bond. Okay. Okay, so that looks good. And we can look at the same in a triple bond hydrogen cyanide. Nasty chemical. Here's the Lewis diagram. We've looked at that before. So we are going to see that the carbon is sp hybridized. So in our framework, we have the sigma, the carbon sp with the nitrogen 2p. You see there's a few little shorthands going in here. And then sigma between the hydrogen 1s and the carbon sp. Then we have these two other p orbitals on each carbon and each nitrogen, and they're going to overlap. And that's how it works. And you can try 2-butyne on your own. You're just separating, you're kicking out a hydrogen with a carbon. Okay. Then we have examples for formaldehyde, which we've looked at that Lewis structure before. So you try that one on your own, and you can try propene and propyne on your own as well. One thing I should mention, as I see the word line structure here, sometimes in the book you're going to come across something like this. You're going to say, what the heck is that? Well, that's propane. The lines, each line end represents a carbon. So that's propane. If I have like this, then that's propene. Okay. If I have this, 1, 2, 3, 4, 5, that's pentane. And then I can have 1 pentene, 2 pentene, things like that. So I don't like using that method, those line structures, but if you're doing lots of organic chem, then it is a helpful thing to do. So it's worth your while to spend 15 minutes one day and Google what are line structures for organic chem, just the simple ones, and take it from there. So let's push on a little bit in this class and start looking at what happens if Lewis structures just fall apart. What if they aren't good? Okay, we're talking about all these sigmas, all these pi's, all this stuff. What if it doesn't work? What's a better way? Should I say better? Let's not say better. What's another way to describe the bonding in a molecule if Lewis structures come up short. And we have what's called MO theory, molecular orbital theory. We're going to look at it mostly at diatomic molecules. We'll sneak in near the end of the chapter some larger ones. But we're going to start with diatomic molecules. And what you do is you create molecular orbitals. So the whole properties of electrons are said to be delocalized. And those delocalized electrons occupy molecular orbitals because they may span entire molecules. Okay, so we'll start with hydrogen. We talked about the overlap of the atomic orbitals in hydrogen. Now, when you overlap, a mathematical treatment means that the total number of molecular orbitals produced by a set of interacting atomic orbitals is equal to the number of interacting atomic orbitals. So if I bring a hydrogen on one atom, its 1s orbital, up to a hydrogen on another atom's 1s orbital, then I get two molecular orbitals. And we get what's called a bonding orbital, a bonding orbital, and a non-bonding orbital. So the bonding orbital in the molecular orbital theory is called a sigma, and the simplest one, so sigma 1s. The anti-bonding orbital, where we subtract amplitudes, is called a sigma star 1s, and that is known as anti-bonding. Later on, we'll also look briefly at something called non-bonding. So sigma 1s is a bonding molecular orbital, the simplest possible one, and sigma star 1s is an anti-bonding molecular orbital. And here we see a molecular orbital diagram. So we have a hydrogen here, They talk to each other, the 1s atomic orbital on each, and create this set of molecular orbitals, and the two electrons go to the ground state in our unexcited hydrogen molecule. Okay, the labeling is still sigma because the concentrations are along the bond axis. Okay, so I drew a molecular orbital diagram. The Aufbau principle, the Pauli exclusion principle, Hund's rule, they have to apply no matter what types of orbitals they occupy. We'll see that in a second. There isn't anything in the sigma star 1s, therefore you don't put any arrows in there. Now, if I wanted to go to helium, well, helium would be 2 electrons. If I have helium molecule, He2, that would be 4 electrons. So I put 2 in the sigma 1s and 2 in the sigma 1s star. Okay, so you're going to say, there's a destabilizing effect. That may cancel the effect of the bonding electrons, and it does, and we can get the bond order. So the bond order is a way to describe what's happening between the two atoms. So the equation is bond order is 1/2 the number of electrons. Okay, sorry. Is that parentheses in the right place now? Let's see here. Oh, I have here something that is interesting there. Okay, we're going to count the number of electrons in the bonding MOs, which is 2, minus the number of electrons in the anti-bonding MOs, which is also 2. So 2 minus 2 is 0, and 1/2 of 0 is still 0. So there is no bond in dihelium molecule. Okay, helium, in normal situations, does not form a molecule. Hydrogen, H2, so it'll be 1/2. Well, there'd be 2 electrons and no anti-bonding ones, so the bond order is 1. So bond order, yes, unfortunately, some people call it BO. BO of hydrogen is 1. BO of helium is 0. Bond orders typically are natural or whole numbers, so 0, 1, 2, 3, but they can also, strike that. They can be fractions too. Okay, they can be halves, thirds. You don't get really weird stuff, but they can be halves, thirds, quarters. Okay. Yeah, non-integer bond orders are possible. if you get a bond order with a value of 1.5, then you say that the strength and the length is somewhere between a single and a double bond. So, does He2+ exist? So this is example 7.8. Well, I'm not sure if it exists or not. Let's see. That would be 3 electrons, right? So you'd have in your, almost like a terrific trapezoid, but just focusing on molecular orbitals. So we put 2 electrons in the sigma 1s, and then 1 electron in the sigma star 1s. So it's going to be 1/2 of 2 bonding minus 1 antibonding. So 1/2 of 1, so it's a half. So yes, helium 2+ cation does exist. The bond order is 0.5. Okay. And that is true. We have here, which species has the stronger bond, H2 or H2-? Well, it's going to be H2, right? Because H2 bond order will be 1. H2-, you're going to have an electron in the sigma star 1s, so it'll be 1.5. Sorry, it wouldn't be 1.5, it would be 0.5. 2 minus 1 is 1. 1 divided by 2, so 0.5, right? 0.5. So H2 would have the stronger bond. Okay. So you can try these practice problems on your own, 7.27 and 7.28. What about, second row diatomic molecules? And the story here really depends on how many electrons there are. So we were just looking at first row, hydrogen and helium. Now we can look at second row. And we can set up a ordering here. They're just describing sort of the build-up on how things happen. But let's get to the nitty-gritty of it all. So you can have p orbitals going head-on or side-on, and you end up with different overlaps. And we're going to draw a chart in a minute. Some conclusions, though, with 8 molecular orbitals generated by n equals 2 atomic orbitals. So the bonding and antibonding sigma s orbitals are more stable than any of the 6 molecular orbitals derived from the 2p orbitals. So the sigma s are going to be lower down on the hierarchy. They're more stable. And the 2 pi bonding orbitals are degenerate. Degenerate, we used that term before. They have identical energies because the corresponding atomic p orbitals are degenerate. And the pi star orbitals are also degenerate. The antibonding orbitals formed from the atomic 2p orbitals are at the top of the energy level diagram. So here's an energy level diagram for oxygen. And it's true for any, these are homonuclear diatomic molecules, where the atomic number of either atom is 7 or more. And you're usually given a chart like this on a test. So notice I'm just drawing the valence electrons here. I'm not putting in the core ones, the n equals 1. So if I'm looking at oxygen, there are 12 valence electrons, 2, 4, 6, 8, 10, 12. So what you do is you fill up the sigma s with 2, the sigma s star with 2, so that's 4, the sigma p with 2, so that's 6, and then you fill up the px and the py, so that's 8, 10, and you got 2 left, and you use Hund's rule, and you put 1 in the px, the pi x star, and 1 in the pi y star. You aren't filling up the sigma p star. So this is the order in which you fill up for oxygen. If I want to get the bond order, it's going to be 1/2, and again the core electrons cancel out, so I can just look at the bonding ones. So it's 2, 4, 6, 8, and the anti-bonding ones are 2, 3, 4. Remember, that's that up to 12. So 4, So the value is 2, and often the bond order matches whether it's a single, double, or triple bond. So oxygen is a double bond, and we see that the bond order is 2. What's interesting here is just looking at the Lewis structure, you think everything would be paired up and oxygen molecule would be diamagnetic. Right? We used that before in a previous chapter, but it's not. Oxygen, in fact, is paramagnetic. It's not diamagnetic, it's paramagnetic, because you see here, when we look at the molecular orbital drawing, that the antibonding molecular orbitals each have 1 electron in them, which are unpaired. So there's 2 unpaired electrons. If you have at least 1 unpaired electrons, it's going to be paramagnetic. And this was an interesting motivation to look at molecular orbitals. Okay, if we wanted to write the electron configuration for the valence, I could do it like this: 2, 4, 6, 8, 10, 12. Right, this is the valence. So sigma S2, sigma S star 2, sigma P2, pi X2, pi Y2, pi X star 1, pi Y star 1. You could put a 2 in front of all, like sigma 2S, sigma 2P, but if it's the first time you're looking at it and you know you're in the second row, you could just leave off the little 2 in front of the X's and Y's and S's, and it'll be okay. Evidence for antibonding orbitals, I just mentioned that, about the paramagnetism, and so that's good. If I take away an electron, so from O2 to make O2 plus, notice that the bond gets smaller because it's a little less antibonding, right? Antibonding means it doesn't want to be bonded. So if I take away an antibonding electron, the bond length goes down and the bond energy goes up and the bond order goes up. So it all merges nicely together. Okay, so that extra complexity explains features that a simple description doesn't explain. And life's like that sometimes, isn't it? So, if we're talking about homonuclear diatomic molecules, which we just did looking at oxygen, there is a slight variation depending on how many electrons there are. And 7 electrons per atom is a turning point. So, if I go straight, rather than looking at all the diatribe, you can look at it. Let's just look at the picture, and usually I give you a picture somewhat like this on a test or quiz. If the atomic number is 7 or less, so nitrogen or less, then I fill up sigma, sigma S, pi, sigma P, pi star, and sigma P star. Okay, so for boron, which would have how many valence? 6. Boron's in group 3, so 6. So it'd be sigma S2, sigma S star 2, then you'd have a pi in each one. Okay, which means that B2 better be paramagnetic. Let me jump up here. Contradiction to this prediction, B2 molecules are paramagnetic with 2 unpaired electrons. That's good, okay, but notice with oxygen, the only difference in terms of ordering up is that you're going to fill up the sigma P before the pi. Okay, if you're nitrogen downward, you fill up the pi before the sigma P. So they are 2 characteristics. If it's a heteronuclear diatomic, there's similar charts. I'm not sure if we're going to get to that. Okay, so that's the difference between the two. So use MO diagrams to explain the trend in the following bond energies. B2 is 290, C2 is 600, and N2 is 942. Well, we sort of talked about that in the crossover point. So here's B2. This is just the valence. Really, there's no need to talk about the inner electrons because, I mean, if I did, I'd have 2 up and 2 down. Yeah, but I mean, that doesn't help us answering the question. So here I see that I have 2 antibonding ones, and so the bond order is 4 minus 2 is 2 divided by 2. The bond order is 1 here, right? Or is it 0? Let's see. 2, 4 minus 2. So that is, there's some extra lines drawn in here. I don't know why I was writing on that. I probably shouldn't have. Yeah, it just stops here. So 4 minus 2 is 2, divided by 2 is 1. So the bond order is 1. C2, 2, 4, 6, 8, right? So 6 minus 2 is 4, divided by 2 is 2. So the bond order in C2 would be 2. Nitrogen is, we haven't got to the crossover yet, have we? 2, 4, 6, 8, 10. Yes, and so I'm going to have 2, 4, 6 minus, no, 2, 4, 6, 8. 8 minus 2 is 6, divided by 2 is 3, so the bond order is 3. So it makes sense that the bond energy will be greatest for the molecule with the greatest bond order. And that's what we see happening there. Okay, only nitrogen exists under normal conditions. The others would form solid networks rather than isolated diatomics. But under the right conditions and vapors, it can work. N2, O2, and F2. Well, we did N2. It was 942. O2 is going to be weaker because with O2, now you're going to, well, we did O2 way up here, didn't we? There's going to be 12, so it's going to be 2, 4, 6, 8, 10, 11, 12. So you're going to have these antibonding ones. And then if you go more, what's the next one? Fluorine. Then you're into even the antibonding up there. So fluorine is going to have more antibonding orbitals, back to a bond order of 1, and so it's going to be weaker. Oh, we do decide to talk about heteronuclear diatomics. Okay, some years we don't, but I can do it here. Heteronuclear diatomics, so the atoms are different kind. When we use these crossover points, well, let's see, NO, we're going to put this sigma. Oh, you look at the average. So average of 7 and 8 is 7.5. So you're going to fill up the sigma first and then the pi. So that's how you work it. So for NO, it's almost the same as O2, except instead of a pi y star 1, you don't have anything, but you got 1 less electron, and then you can calculate the bond order. So it'll be 2, 4, 6, 8 minus 3 is 5, divided by 2 is 2.5. So oxygen has a bond order of 2, NO, which is going to have 1 less electron in an antibonding molecular orbital. The bond order is 2.5. Nitrogen, well, then you've even better, even less electrons in antibonding MOs, and you get a bond order of 3. So to summarize it, you could say that the sigma p is lower than a pi set when the average atomic number is greater than 7, and pi is lower than sigma p when the average atomic number is less than or equal to 7. Okay? So N2 is going to have a higher first ionization energy. It's just a more stable molecule than NO, and CO is in the middle there. So NO ionizes more easily. So if I go to the electron configurations based on those rules, and I'll let you set that up, let's just look at them. So NO, fill them up. This is again the valence, right? I'm going to have 6 and 5, 11. 2, 4, 6, 8, 10, 11. That's NO. And 2, CO. I'm going to fill up the 2, 4, 6, 8. What's the average of 6 and 8? 7, all right? So I should fill up the pi and then the sigma p. Yeah, that's right. Same as N2. Good. NO, I'm going to 7.5. I'm going to do the anti-bonding before the sigma p. Right. Okay. So we see that CO and N2 are actually isoelectronic, aren't they? They both got 14. So NO has that one less electron, so it is going to ionize more easily. It's less stable. N2 is a bit more than CO. There's some other reasons for that. Are we going to explain those? Let's see. Comparable ionization energies. No, we aren't going to go into that much detail. But it's much easier to remove the antibonding electron from NO than it is to remove a bonding electron from either of the other species. Okay, so that's an interesting idea, isn't it? I mean, we've mostly been talking about ionization energies of atoms, but you can do the same for molecules, and it's easier to kick out a valence electron in an antibonding orbital than it is valence electrons in bonding orbitals. And you can try practice exercise 7.10 on your own and the section exercises. Okay. Dilithium molecules, look at that because that reminds me of Star Trek and dilithium crystals. So we'll get to 3-center pi orbitals next time. Have fun with all this.